Hello everybody. So in this video we are going to just solve some practice problems on the fluid statics concepts that we covered in the previous few videos. This is going to be very helpful to get more understanding of the concepts and apply them on real problems. The first problem that we have here is about a piston that is in a piston cylinder device. So this is the piston, and there is a cylinder, and there is a gas that is uh, in the piston. It's in the cylinder. So this is the piston is not leaking, so there is no this air inside is kept inside, or the gas inside that's kept inside. The piston has a mass of 40 kilograms, and its cross-sectional area is 0.012 meters square, and the local atmospheric pressure is 95 kilopascal. So it seems that the experiment or this device is put at high altitude, so the pressure is 95 kilopascal. It's not 1.013 or 101 kilopascal, it's 95. The gravitational acceleration is given, and we need to know the pressure inside the cylinder in psi and psi gauge. So this problem is kind of an easy one, but there is a point that I want to make clear here, and this is a good chance to discuss this thing or this point, that for a cylinder like this, there is part of the gas that is at or directly below the piston, and there is a part of the gas that is at the bottom side of the cylinder. So there's difference in height between the two points, and you might think that we need to specify exactly where we want to calculate the pressure, because the pressure here is going to be different from the pressure here because of the head of the gas. It's rho gh term. But this is right if it's liquid, but in gases, since the densities of gases are very low, for instance, the air has density, it's 10 power minus 3 the density of water. So the liquids are in general much more denser than the gases. So we ignore the head or the pressure due to the height of the gas for the regular heights, and if it's 1 meter, 2 meters, or it's something in this range, we ignore it. And we already saw this in the previous video when we were discussing the atmospheric pressure. The atmospheric pressure will start to be felt. The decrease in the atmospheric pressure will start to be felt at high altitudes, like 1000 meters or something. So if it's 1 or 2 meters, it's not a big deal. The amount of pressure due to this 1 or 2 meter is going to be very negligible compared to the pressure that we deal with, like the atmospheric pressure here. So we consider the pressure everywhere in this container or in this cylinder equal. So it's the same pressure everywhere. So this is why we didn't specify the point that we want to calculate the pressure at, because the pressure is the same everywhere. So anyways, we want to calculate the pressure. So the pressure would be a result of two sources: the atmospheric pressure and the pressure due to the weight of this piston. So the atmospheric pressure is already given as pressure, so there is nothing we need to do about it. For the weight, we have to first calculate the force and then divide the force by the area to calculate the pressure. So we have the mass, the area, the pressure, and the pressure as absolute pressure. It's the atmospheric pressure plus the weight over area. The weight is mg, and the area is already given. We substituted here with the pressure in Pascal to make the units homogeneous. So this is Pascal, this is Pascal. So this is the pressure in Pascal. Of course, this is the absolute pressure because we included the atmospheric pressure here in this part. We want it in units of psi. So to convert atmosphere or the Pascal into psi, we know that 101 kilopascal is equivalent to 14.7, almost 14.696 psi. So we use this conversion factor to convert this from Pascal into psi absolute. If we want to calculate it in PSI gauge, then the only difference is that we are not including the atmospheric pressure, but the steps are going to be the same. The pressure is only due to the weight over area, and then the gauge pressure is the conversion of unit from Pascal to PSI gauge is the same unit conversion that we did before. So it's a simple problem. It's a straightforward one. The next problem is easy as well, but it's from my experience with the student, it seems to be a little confusing, and I think it's confusing because they or the students find it hard to imagine what happens here. So just to give you an idea what we have here, there is a reservoir. Let's say it's a big container that contains water, and there is a cylinder that is a hollow cylinder, okay, and it's put so that it's vertically put in the container so that part of it is immersed in the water, and the rest is above the water surface. And now we have a piston here, and this piston is pulled upward. Okay, so when it's pulled upward, part of the water is pulled upward in the cylinder, okay, and it reaches a height h due to a force F. So I think the problem that the students have is they cannot understand how can water flow upward. So just to give you another example that is going to be easier to understand. Imagine that this piston is pushed downward. So if this cylinder goes deep down in water and then you push the piston downward, then the piston will be somewhere here, and the water level would be less than the water level here. Okay, so the reason that the piston is pushing the water downward is the force is downward, so it's applying more pressure to push the water downward. Here it's the opposite, so it's pushing pulling the piston upward is going to pull water upward as well. So it's just putting a negative sign, so its negative force will get the height of the liquid in a negative in the opposite direction. So instead of having the height here, it's upward, and the force is upward. So it's the same concept. So I hope it's easy to understand now. So the problem is just about we are given the diameter of the cylinder, and the problem is about calculating the amount of force needed to raise the water to a height h of 1.5 meter above the free surface. So in the fluid statics problems, and I think this is one nice thing about the fluid statics, that there are just two concepts that we or two laws that we apply. And we apply them to every case of fluid statics. The first is that 2 points at the same elevation in the same continuous fluid will have the same pressure. Okay, and the second is 2 points at different elevations in the same connected fluid will have a difference in pressure of rho gh. These are the only two rules or the two laws that we are going to use. So the main thing that we need to do here is to specify points that we know information about, whether 2 points that are at the same elevation or 2 points at different heights, and we will try to find the missing part or the missing information through these two things. So if you look here, we can specify these 3 points, A, B, and C. So point A and point B are at the same height. Point B and point C have difference of height h that we are interested in and we want to calculate. So what we know is A and B are at the same elevation in the same connected fluid. So the pressure at A, which is open to the atmosphere, it's atmospheric pressure, it's equal to the pressure at B. So we know that the pressure at this point is atmospheric pressure. And we know that there is difference of height h between points B and C. So the pressure at point C can be calculated in terms of pressure at point B and the height h. So this is how we are going to deal with the problem. So first we know that PA equals PB, which means that PB is the atmospheric pressure, and we have a relation between PB and PC that PB is PC plus rho GH. So we can rearrange the equation. We know PB because it's atmospheric pressure, so we can calculate PC in terms of PB. We will just rearrange the equation. PC is PB minus rho GH. Okay, so this is the pressure at point C. So we already know the value of the pressure at this point. Okay, and now given that this point is at the bottom side of the piston, so this point, the pressure at point C, is a result of all the pressures above. The pressures above are the atmospheric pressure, because the whole setup is in atmospheric pressure, or under atmospheric pressure. So there is atmospheric pressure applied here, and there is this force. Of course, atmospheric pressure is pushing downward, and the force is pulling upward. So they are in different directions. So the pressure at point C is the atmospheric pressure minus F over A. Okay, and this minus is very, very important. Otherwise, if we put it positive, then the force would be acting in the same direction of atmospheric pressure, which will be a totally different problem. And of course, we know the area, we know the atmospheric pressure, so we can just substitute with all the numbers that we have to calculate the force, which is 1040 newtons. So this is the second problem. The last problem is about a hydraulic press, but it's kind of with a small tweak here. That in the hydraulic press we used to put a piston here to push, and that force that we apply here results in larger force on the other side. Okay, so here we have the same thing, but instead of having a piston on this side, we have fluid, like a tube that's filled with the fluid, and the fluid head is what applies the pressure. Okay, so we have here a load of 500 kilogram, and we know the specific gravity of the fluid is 700.78, and that thin tube has a height h that produces force that is enough to raise the weight. Okay, to push it upward. So we need to know what is the height h that would be enough to raise this load. So again, it's a fluid statics problem, so we have only two things. So I think the main skill that we need to acquire here is to know how to specify the points. So we have point A and point B. We picked point A because and point B are both at the same height, but we picked point A because it's directly below below the piston. So the pressure at point A is already known. It's the atmospheric pressure plus the weight over area. So know the pressure at point A, and we know that the pressure at point B is equal to the atmospheric pressure plus rho gh. Okay, so it's simple. So we can put point A and point B equal to each other because they are at the same elevation, the same connected fluid. We have the pressure at point A is the atmospheric pressure plus the weight over area, which is g over area, and the pressure at point B is the atmospheric pressure plus rho gh. So putting them or all the equations together, this is PA, this is PB, and both are equal, so we can combine the equations, and then we can find that W over A equals rho gh. And the W is mg, so the g will cancel out, and then we can find h as m over rho A, which we can calculate to be 0.55 meters or 55 centimeters. We can solve it this way, or you can think of it as we used to do before in the hydraulic press before, that you can say that the force over area equals force over area because the 2 points have the same pressure. It's the same thing. So you can say that FA over AA equals FB over AB, and then we know the force at point A is the mg, and the force at point B, of course we will ignore the atmospheric pressure because it will cancel out in both cases, and the pressure at point B is rho g h. Okay, times the area, of course, rho g h times the area. So because rho g h is pressure, so multiplied by area, so it's rho vg, which is rho a times h. It's the same thing. And at the end of the day, we will reach the same thing, that h equals m over rho a, and we'll get the same result. So whether you like to put it this way or the other way, both are going to give the same result. So I hope these problems were helpful. Next time we'll start one other really interesting application of fluid statics, which is the YouTube manometer. So we'll see you then, inshallah. Goodbye.